In this video, I present active shape models as a method of representing and segmenting objects in images. Recent work in computer vision is about generating high-level descriptions of an image. For example, that an image shows a group of people waiting for the bus. On the other hand, if we go 20 years back, the problems we were trying to solve was typically separating white objects from black backgrounds. Thresholding algorithms can solve these problems quite well, and they were able to run fast even on low-end hardware. But oh, wait! We're trying to find a dog in what would appear to be a random collection of splats to someone who has never seen a dog in their life. We can't expect a computer to solve this problem if it doesn't know what a dog looks like, or even that we are looking for one. Object segmentation can be improved by making use of knowledge we already have about the shapes of the objects we are looking for. This is done by the authors of a popular paper published in 1995. They solved the segmentation problem by representing objects using shape models that are learned from example data. The model used in the paper is a set of ordered points along the object boundary. But, as you might expect, where there's one resistor, there's typically many more, and none of them will look exactly the same. They include this uncertainty in their model by repeating the labeling process on several resistors. After labeling each resistor in the example set, we get a statistical distribution that describes what a typical resistor might look like and what variation we can expect in the image. In the final step, we search for the model that best explains the image data. This search is split into two alternating tasks. First, determine a global transformation that aligns the model with least amount of error against a set of detected points. Due to uncertainty in the exact shape boundary, this transformation will not be perfect. A second step determines a set of local variations applied to each point in the model that gives an even better fit. The local variations are constrained so that the resulting shape is still within the point distribution model. This means that each point in the model is constrained to move in certain directions that are not independent of the other points. These directions are computed by performing principal component analysis on the example set. A subset of principal components is picked out to approximate the space of possible shapes. By varying the strength of each component, we can generate new shapes. Finally, here are some of the applications of the concept presented in this video. Some researchers decided to model boundaries of shapes as well as their internal texture. They used this to fit 2D face models to an image. At the SIGGRAPH convention in 2015, a group of researchers presented their work on the real-time expression transfer for facial reenactment. This year, they have extended their results to only require color input. The techniques they use are based on the same concepts I've presented in this video. They use scans of different faces and generate a statistical face model for the geometry and texture variations. They use principal component analysis to describe the space of plausible faces, much in the same way as we did for the resistor. In this video, I've skipped a lot of technical details, and I've also skipped all of the drawbacks of the method. The paper I presented is 20 years old, so you can expect that much has happened since then. If you would like to learn more, there's a very good book on models and learning in computer vision, which is freely available on the author's homepage. There are also some video lectures on YouTube by a researcher who has published several papers related to the topic. Thanks for watching.